My name is Boguslaw Cyganek. I came from Kraków, Poland, and I work at the HGH University of Kraków. So for over 30 years, I'm a scientist doing research in computer vision, but also writing a lot of software for computer vision, now using also all the classifiers, AI, things like this, but also very deeply in industry programming, and because I work at the Department of Electronics, I do some embedded stuff. So because I'm a scientist, so we used to create some experiments, test beds. So today I'm going to present you such a test bed, which is a project of a compiler, but don't worry, it won't be C++ compiler. So let's go. So it will be a Ford compiler. Yeah, you like it? So how many of you ever heard of Ford? Yeah, I'm surprised. I'm surprised. Actually, my journey with Ford was something in 1990s. I was a student. We were just a developing country at that time, and I wrote to USA to FIG Ford group, and they sent me a diskette, 5¼ inch, and it was Ford. And I was playing with that, and then I forgot about that, and then I recalled it after. I will mention when. Okay, so we will go with Ford, but so this is our test bed, some experimental framework, but our issue is to show some cool new C++ features working in such a project, and why we did it, and what we can gain from it. So you will learn 2 languages today. So one is C++, you know, and Ford a little bit more. So we are in the embedded world. So if I am to say one sentence, it will be that one: enhancing functionality with coroutines. So it will be probably the core of this talk, but later on. And novel features. Coroutines, as I mentioned, ranges, modules, concept, contracts, maybe. Chrono, novel bit operations, so I will touch upon these things. And porting to a real embedded platform, and also about teaching modern C++, because I work at the academia, we teach C++, so we are looking for such projects where we can show new features for students so they can play with this, not too big projects, but big enough to show something in real applications. Okay, so short intro to Ford. So Ford is, I would say, functional language, functional programming, because it is composed of words, and the second feature is it is stack-oriented. So it was created by Charles Moore around 1970, when he was working at the astronomy observatory, and he had to control telescope angles. So he wrote this Ford stuff just to talk with the computer at that time. But remember, 8 bits, I remember processors with 4 bits only. 8 bits was for years the standard of processors. Now we have more, so that was the time. Okay, and let's move on. Oh, okay. Okay, so Ford is joining interpreter and compiler. This is a nice thing to be able to talk with the framework. Okay, and it is based on words. Once we have a set of words, we can compose new words based on previously defined ones. And it can be words can be created, tested, redefined, etc. Okay, and all syntactic elements are defined as words. And the second thing is a stack. So it is using the stack for almost everything to exchange data. And this leads to so-called reverse Polish notation, so we avoid parentheses. So where is Ford? If C++ is somewhere here on this IEEE Spectrum magazine ranking list, So Ford is low, somewhere below that. But what Stephen Cass, who is just maintaining this ranking list, he wrote such a thing, languages that dropped out included Ford, a personal favorite of mine. That's still popular with folks building 8-bit or retro systems. But I will show today that it can be used in modern systems as well, under certain circumstances as well. And if we go to Tiobi, well, we are lucky in the first places. And when we go to another 50 languages, so Ford is somewhere there. Okay? So it is on the list, but it is going down and down for many reasons. But so why Ford? To show non-trivial examples of modern C++ in action. Project for teaching C++. That's a good thing. Maybe you remember my talk from 2023 on teaching, is it a job or a mission? So following this way of preparing projects, Ford falls into this domain. Useful calculator. I use this every day. I attach this to the calculator button on my laptop. Whenever I press it, I have this Ford, and I can do some fast programming, even faster than with Python. Embedded word. And simple OS. That's the key issue. So if we have such simple sensors, let's say, is it a way to put Linux inside and a lot of code, etc., instead of something what can be simpler? Or even go bare metal with such boards? Or do some hobby stuff? So all this, Ford is good for, I would say. So a very, very short intro to internals of Ford. Ford is different. So Ford contains data stack, as I mentioned, and word dictionary. You will see it in a moment. So seeing these two basic building blocks, you can say, hello, I'm able to program this quite easily in modern C++. I take a stack, I take a map, and I'm done. And indeed, this is the core of Ford can be made, let's say, in a couple of lines. But we'll see. So what we have, stack is forever here, for every operation. So this is last in, first out structure. We put something on top, and the basic operations for a duplicate of the value are all arithmetical, logical things are done on the stack, but only on the top, or on a couple of elements on the top. So we can swap the elements, like you see here, after adding them. We can make an over, which is a copy of one element down. And there is another one, rotation, which moves everything down, and the bottom line, the bottom object is going on the top. And we can, again, add something, multiply. You see no parentheses here, because this is our reverse Polish notation, and we can drop, and we have. So these are the basic operations. So when you start learning Ford, you start from this. So you have to switch your mind when you do operations, just to think in this reverse RPN. But, well, maybe older of you remember some Hewlett-Packard calculators. They can operate in this mode, and you can be very fast with this way of thinking. So this is Ford. Okay, so implementing looks like straightforward. Okay, we'll see. So let's take stack. We can take the stack from the standard library, and also we can benefit from stack going to be const_exp later on. This is very important in embedded world. Going to const_exp wherever we can. But we would like to be more flexible. You will see in a moment why. So I implemented this stack 4 with a couple of parameters. So maybe this can be useful for you. Certainly, this is like a very big beginning definitions. But what is interesting here, I would like to have an option to define the stack either on the stack of the computer or on the heap or other memory. I will talk about memory management later on. So how to make it in one data structure? This is the key issue. Maybe you know this, maybe not. This is very useful because based on the, this is my conditional type, yes? So based on parameters from the template, I can have, in one data structure, I have conditional. So depending how big the stack is, it can be either way on a totally different memory space. And quite useful, again, everything can be whatever it can be is const X, and we have all these attributes like non-discard, they help to make code cleaner and etc. So we'll see some. But, okay, so we have the stack, and we can now implement all this duplicate, swap, etc. quite easily, but it will be slow. So for performance, I would like to embed all these operations into the stack, but how to make it without obliterating the purity of the original base stack? So what we did is just defining such classes based on some base, we'll see in a moment what, and we assume that we have a direct access to the stack. Okay? So instead of calling some external function for drop, we are doing this drop just manipulating internals of the stack. So we must be able later on to access this stack. Or for example, the duplicate is just that. And we can make more such template classes, and here is why, because we can make such a thing. Okay, so that can be very useful in practical operations. So this is wrapper types. These are actually mixins. Yeah? So you build, but thanks to this, you can take the stack, you can operate the stack, but you can also superimpose some layers upon this. So this is also useful technique. And now we are with word dictionary. How to implement word dictionary? So look at this, how it is working. So we have a name of a word, and we have a function to call. So we have a map, actually. So this is the basic structure. But once we define a word, we can define another word, which is double drop, just calling the previous one, and so on. So this is the issue. And we access the stack. So that's the natural data structure in C++ to use it. Okay, so this is already what I said, but okay, so we rely on some kind of a dictionary, which can be an ordered map here. We have the key, and we have the value. And the value is a composite design pattern. You will see it later on, just to be able to compose words based on previous words. So it is a recursive structure, very useful in such situations. Okay, so composite, yeah. Okay, what's next? Ability to define your own words. So now we go further on. We wish to define words in Ford. Okay, so to define a word in Ford, I devise a name for it. So I would like to calculate the fuel consumption of a car. So how many liters per 100 kilometers? So to define a word, I need to put colon and semicolon. And everything inside will be calling another words previously defined, and so on, and so on, and so on. So you see the composite here. So this is the comment for the word. So I have liters and kilometers on the stack, and when I return from this function, I have liters per 100 kilometers computed. So what I do, I swap liters with kilometers, I put 100 in floating point representation on the stack, I multiply floating point, I swap again, I divide, and I print the value. So this is the way. Now you know how to define your own words in Ford. So, and this is also a Ford comment with such a backslash. So the syntax is like this. So the question is how to write software to process such a syntax. So we will see few elements of this system in a moment, but we need to parse it and process tokens and so on. So yeah, I already mentioned that. Okay, so software architecture. So I will not go into details of this. Software is available in many versions, so you can download it and play with it. But we have three main building blocks. well, composed as classes. So the basic one is tfort, which implements just the stack and dictionary and couple of words, built-in words. Then we have Fort interpreter, so we can write something, we can talk with Fort, but not yet defining new words with this colon, semicolon. And to define the new words, we have another third class. But what is the virtue of this software architecture? You can cut it out. If you have a small embedded system, you can take only the first part. If you need to talk with your smoke detector, you can take green part. And if you need to put new words inside, then you can take everything. The hierarchy of words, this part on the right side, is bigger, but only because we have many words. I was adding new words inside. But the key issue is we have the base word, which is abstract class, and for all composites structures, for all statements like if, else, then, like do, begin, end, we use this composite. So this is a hierarchical structure. Okay, so how does it work with such hierarchical structures of statements? So if we have something like my word and it has if, then true branch, then else, then false branch, and then. This is the syntax of for. So what we do, we split it. We split it and recursively, and we select the true branch, and we apply the same procedure again, and again, and again. So that's in a recursive way. So it is simple in implementation. Maybe there is a couple of lines of code, but this is how it operates. So once you split into do loop, then you take inner part of do loop, and you call the same function to make this parsing and processing. And it works fine. So few modern C++ features in actions, finally. Okay, so coroutines. For cooperative OS, that's the key issue. Why? I will tell you why later. We have ranges as well on board. Few more hints, spaceship operator, no unique address is helpful. So start lifetime as, so the domain of bit operations in projects like this, embedded stuff is quite useful. So, new kid on the block, coroutines. Today, Nico had a presentation on generators, so I knew that, so I accomplished to put myself with this presentation somewhere in between, but certainly I will not talk about coroutines in depth. I will just touch upon the subject, but I can recommend also, apart from Nico talk, I can recommend this talk by Andreas Fertig, and also by Andreas Weiss. So I like these presentations, and then you just play with the code, and that's the best way. There are many blogs, but I recommend starting from Louis Baker. This is the seminal, let's say, blogs or papers on the subject. A coroutine, what is a coroutine? Is a function that can suspend and be resumed later on, okay? Important for this project and for many projects is that they are stackless. It can mean many things, but the most important thing is that you cannot suspend from inside the stack when you call. Okay, you can call functions from your coroutine, no problem. You are building stack frames. But when you call co-await, this is only from the base level of your coroutine. You cannot call co-await from somewhere inside. If you call from somewhere inside, this is another coroutine, okay? So this has implications in such a system like this. I will mention this later. So if we conceive a function like a state machine, then this is the natural function, normal function, and this is coroutine. So you see the differences. So a function, you start and you finish, and you are done. But with coroutine, you start, then you can many times suspend and resume. So it works like this. But this stateless has many consequences. Okay, but from the syntactical point of view in C++, Coroutine is something what contains at least one of these new keywords, co-await, co-yield, or co-return. But between us, understanding coroutines is understanding co-await. Just forget about the other two. Okay? If you understand how co-await is working, you understand coroutines. Quest for Cooperative OS. What is Cooperative OS? Anyway, we have multitasking. Even on my mobile, we have plenty of threads, cores, etc. Why we are going past the times? Okay, but sometimes it is useful. So what is cooperative? It's not preemptive. A version of multitasking in which operating system never interrupts a running process and doesn't make a context switch to another processes. This has implications. I'm teaching operating systems to the students, and I'm showing how many screens of assembly code are required to make a simple context switch. For example, for PowerPC, these are 2 screens of push, 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 something, reading a flag, pop, 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 pop. And all these pushes and pops just access external memory, which is sometimes on modern machines, it is even 2 orders of magnitude slower than internal registers of. So if we can avoid this, it's worthy considering. Okay? But what instead? Instead, processes agree on some protocol to yield control and must cooperate. Otherwise, if one breaks, everything breaks. So it relies on regularly giving up time. So you will see this in implementation soon. Okay, but the virtue of this is it doesn't require context switching nor thread synchronization. Okay, so I came across this paper many years ago, and this is proto-threads. So what are proto-threads? According to this paper, a novel, at that time novel, programming abstraction called proto-threads that make it possible to write event-driven programs in a thread-like style with a memory overhead of only 2 bytes per prototype. So that was the first attempt I found on making such things in embedded systems using C, C++. So how does it work? Have you heard of this DAF device? That's interesting. This is also useful if you teach coroutines. Once you understand the idea of DAF device, you see, okay, my coroutine is working this way. Okay? So how does it work? Let's make a range of values. So from to, okay, so simple function like this. Does it work? Well, it works, but doesn't produce what we expect. It will return I. All the time I call this function, I will have 1 value returned. Yeah? But I would like to call this function and have another value, next value. Call it again and have next value. How to do this? Okay, so we have this for, and we superimpose. But look at this. Look now. Wow. You see that? Is it possible in C? Yeah, this is perfect code in C and even in C++. It's not UB. So how does it work? So we have switch and for, but this case 1 is inside for. And the key idea is to have statics here, 2 statics, 1 for the counter and the second to keep the state of this function. So the first time we enter, we jump to case 0 and we initialize state to 1. But all the next times, the state will be 1, so we jump here. And we are inside the for, so we get another one. Does it work? Yeah, that's fine. But look at this. If I wish to have 2 ranges, oops, I will have some values, but not expected ones. Yeah? So what to do? But it is possible to this is what proto-threads are doing with some macro stuff. They are producing new static values for each proto-thread, and it works. Then I came across this paper, C++ coroutines and microcontrollers, and it was seminal paper for me in IEEE Embedded Systems Letters. It's not that old, it's from 2021. So what are their findings? They made experiments on ARM Cortex in Internet of Things. So, well, small sensors, bigger sensors, everything. Coroutines for cooperative tasking. They accomplished this. So it was for me, okay, I can do similar thing. Context switching with coroutines is significantly faster than with thread-based real-time operating systems. So this is their finding. But they are good for embedded systems. But the implementation imposes constraints that may prevent its widespread acceptance among the embedded development community. This is what they wrote. Further work should be focused on improving the compiler and language so that fine-grained control over memory allocation can be provided. And indeed, they did their own implementation of coroutines, which I wanted to avoid. So that was my inspiration to put this into forth and see how good the standard implementation of coroutine is and what I can do in this field of cooperating multitasking. But please remember, they have on the GitHub their own implementation of coroutines for some reasons. Certainly, they started before the standard was finished, but anyway. So, coroutines. Again, we know this. We can suspend, resume, we can destroy, call, return, and we have some two spaces to think of. We have a coroutine frame and stack frame. And coroutine frame holds parts of the coroutine activation frame that persist while the coroutine is switching back and forth from the suspension to resumption state. And stack frame part only exists while the coroutine is executing, and what is important here, you see, is freed when the coroutine suspends. So you have to go up your stack, then you suspend. Okay, so it is like a state machine. Yeah. So you can take care. But from the programming point of view, if a traditional function is like this, so coroutine is operating like this. It is in the separate space with its data. So it has one of all, but at least one of these co-await, co-yield operations. It is also possible to terminate it completely. You can call co-return. And coroutine maintains its local stack to manage calls to other functions, but the stack is cleared during suspend. It can be the same stack as the caller stack, but you can think of this as a separate stack. So from the programming point of view, what are the building blocks of a coroutine? Probably the most important thing, what the compiler is looking for first, is promise type. I wrote promise here. So this contains data, and it gives communication between the caller and the callee coroutine. Apart, we have coroutine handle, which is kind of a pointer to that coroutine. We'll see in a moment. Then we have a waiter object, which is responsible for controlling suspension and resumption. There can be additional stuff like iterators. What Nico presented today, generators, he called begin, and because there are iterators, but they don't need to be in the coroutine. They are in the generator. And the unary co-await is usually overloaded in so-called awaitable objects. So you see how many objects are interacting here. This is what makes coroutines a little bit difficult at the beginning to understand. We can go also some bypass if we wish to do a wait operation directly from the promise, calling await transform without this operator awaiters. Or we can split this operation into three from which this awaiter is characteristic of three functions: await ready, await suspend, await resume. And the most important is await suspend. When it is called, when the coroutine is going to be suspended, then the caller is called, something is happening, then is coroutine resumed, and only then await resume is called. So this makes this granularity of calling coroutines. And we have, when we call such a thing like a coroutine, we have such a framework. We have three pliers: a coroutine framework when we create coroutine, so we have a coroutine itself, and we have something returned by the coroutine. Three things. So everything is embedded in some code. So this is the first plier. We have coroutines here, and we have something what coroutines is returning. Okay. So this is coro interface, what coroutines is returning. There can be a waitable which can be passed to the coroutines. Coroutine interface handle and the waitable can be passed, so the procedure has an access. So here is the way. We have coroutines with parameters. We can pass our own awaitable, and this will control how suspension and resumption operations are going on. But we'll see this in a... And we can, from the caller point of view, we can ask if the coroutine is already done. If not, we can resume it, and so on when it is needed. And this is everything in one thread, but can be in multiple threads. But the beauty of this is we can do everything in one thread. So there is much more, but coroutines, examples. So what we have in Ford, what we implemented. We implemented generators. I will not go much inside because we already had the talk by Nico Yosutis. And we have these core fibers for cooperative multitasking. So let's go to the fibers. Well, we know what is cooperative multitasking. So how to implement this? We have semi-fiber, and this is a simplified code, just to fit on the slides, but it gives you the idea. In the code, it is more complicated, but the idea is like this. And we have the simplest core, which is our coroutine framework with all these promise types, etc. So, okay, some debugging, poor people debugging. Then we measure time. We need to measure time, and we do our work. We call something to do something. Do work is some external function. It is not a coroutine. And what we do, we measure time. We measure time, and if our time elapsed, we do suspend always. We can do other kind of we can use other awaiter, but this suspend always is, you see from the standard library, it works in this framework quite well. So what is the difference of this approach? Because we can have an external scheduler, right? But here, the coroutine itself is measuring its own time. So I don't need to take care from the external code. That's the beauty of this approach, I would say. So here the main part goes, okay? So that's the main idea. And how to make this and how to make this time measurements, we'll see in a moment. This is simplified version. So now, okay, now we have to implement this framework, okay? This is this part on the left, yeah, the return value. So this is the main framework, actually. How we define this? The simplest one. You see, we are going to define these objects. So compiler is looking for promise type, yeah? How it does it, it can be controlled by coroutine traits. But you see, we have structure in a structure. So this is what compiler is looking for. Once it finds promise type, it is looking for some characteristic functions like get return objects. So you see here, okay, I'm returning this. So this should be of promise type, but I'm returning the entire framework. How it goes? Okay, there must be a way from promise type to the simplest core, to this external. And indeed, there is. We'll see it in a moment. We have initial suspend. Yes, let's suspend. When we start, we stop the coroutine. Don't run. But we can use suspend never, and it runs immediately. Final suspend, what to do when the coroutine finish? Also suspend always. We have some exceptions, it can be empty, we have some return void. That is the framework, but this is the minimal framework required, which is not that bad. And here we have the way to construct, this is continuation of how to construct from promise the simplest coro. We have a constructor. And we have also the structure. If the coroutine is done, we destroy it. And we need a handle as well to handle the coroutine. So we have all these pliers here. But it's not too much. And do work is, well, something very simple. You will see in a moment something more elaborated, but, well, it is also doing some delay and print something, but it can be any function. But the thing is, this is not a coroutine. So from this coroutine framework, I can call any function. That's the key thing. And it will suspend upon elapsed time, all the time. But also the limitation is I cannot suspend from inside do work. That's the limitation. Okay. So time point, we can use chrono library. I recommend this, if you don't know this, it's quite useful. So how does it work? Let's put this all together. So we create two fibers with some parameters, and we say, okay, first fiber, 100 runs, and 50 milliseconds per each time slice. And the second has 300. Dog is longer and it has longer time. So it is probably more important task in my system, fiber 2. Second fiber 1. Okay, so what we do, if not done, we resume it. Then we can do something in this space of code, and that's it, okay? So if we go a little bit farther, because this is half of this function, so here is again the loop. So we do the same with fiber 1, and look at this. At the end, in the end, we ask if both are done, then we finish entire play. Okay, simple. So how to make it less simple? We can make a scheduler, but the scheduler can be simple vector of coroutine handles. That's interesting. The same fibers, and I can put the fibers into the scheduler. Certainly, in practice, this can be a little bit more elaborated scheduler, but here is some housekeeping lambda function just to resume if this is not done. And if it is done, it is erasing that coroutine from the scheduler. That's all what it does. Okay, so that's the main pliers here. Yeah, and how we do this? Now we manage everything by the scheduler, and we do as long as there are coroutines still to. Certainly, they can be infinite. Yeah? So we do this like here. So results of this experiment. So we are running this. So cats, then let's start dogs again. But look at this. This is not doing its own action. It is doing for some time and giving up, giving back to the caller. And again, certainly these are not all the iterations. So that's the idea. And now we are done. At the end, because the dog had more iterations, the cat was already finished, and the dog still, the dog coroutine still operated. So how to put this into Ford framework? I devised such a word, co-fiber. So without this word, this is normal, ordinary Ford word. If you put co-fiber, you are telling your Ford, make it coroutine. But remember, it is already compiled in C++. So we are now under fourth level. So it must already run. So we have 555 rotations and 75 time slice for each. And we have some operation here, which is toggling, just basic operation for our embedded guys, just toggling your LED. And it must return 1, otherwise everything is finished. So this is a fuse. Just if you wish to break from this worker part, you can break the fiber. Generators, I will not go into the code of generators, as I mentioned, but it is also built into the effort. So now is another word called range, and from what value 10 to 113 with the step 13, and I can make another ID in which I print unique value is equal, my core range, then I print it and I go to new line. So if I call this, I have OK, ID, and unique value is 10 because we started from 10. Then I am again in interaction, I call this unique value, and I have 23 because it is plus 13, and so on and so on. I can be indefinite. So I implemented generators. You can find this in the code on the GitHub, but you can also probably, I haven't tried, you can use this to generate what Nika Josutis was presenting today. Ranges. We have a few minutes. Ranges. Yeah, again, that's the big stuff. I will not explain ranges. We have a lot of presentations even on this meeting this year on ranges. But these are the lectures I like, I learned from them, so I can recommend them. And a lot of materials, but a very short intro ranges since C++20. Extension and generalization of the algorithms and iterator libraries. That intention of the authors makes them more powerful and making them composable and less error prone. So the idea is to make code more clear, more verbose. In some situations, yes. So I will show you some examples. Library creates and manipulates range views, which are lightweight objects that indirectly represent iterable sequences, ranges. So let's start with some very, very simple example, vector with positive, negative values, and we wish to select only positive ones, like this, and multiply them by 2, so we can use ranges like this. Without them, our code will be longer for sure, or we'll make some intermediate variables on the way. So we have the result. But the real cool stuff is just this possibility of joining in pipes. Last year I had a presentation on pipes, so if you wish to go with this, please just go on YouTube and see the recording. So we can write code like this with this pipe operator. Okay, so how do we use this? But before we go further on, so we have a range, which is an object that defines a sequence of elements and providing iterator pair, begin and end. So mentally, this is the range, begin and end. My range, a structure which defines begin and end, is sufficient to have this. Then we have a pair of iterators, or we can have an iterator and a sentinel. That's something very useful in practice, but requires. And a view, which is a lightweight proxy to the range that refers to a subset of objects in a range with a possible transformation recipe. And as Björn Straustrup named this, a view may be interpreted as another way of looking at the range. That's the good thing of seeing views. So we have these features like function composition and lazy evaluation, already mentioned the sentinels, cache as well. So graphically, we start with data collections, and then we superimpose a range or sub-range, just defining the begin end. And we have view, which is a proxy to a range. It has its own begin and end. We have range factories, we have range adapters, we have range concepts, and we have algorithms, and we can use them quite easily also in embedded stuff. So here are some examples. Majority are in token processing. So these are, for example, to upper. So we can take a name and we can pipe it with transform to upper, and then we transform to return value to the name. So it will be a returned value from this to upper function. It can be, ranges can be very, very successful in such processing of tokens like here. So we have some token stream operations. So what we need to do is like a state machine. So we need to find if the line begins with the colon, because we are looking for the defining words. If begins with the colon, if it ends with semicolon. If no colon, then it is calling a word. So how we do this? Simple things. Like this, just for completeness. In the end, we strip ending comments. But the whole thing starts here. Once we have this prepared string, we need to tokenize it. So for this, we use regular token iterator. And we pass only those that are not empty strings. We transform them to token objects. And we create a stream, which is a vector of tokens. How to do this? We can make many loops or big loop, but we can do with ranges like this. We create a sub-range based on this regular expression token iterator, and then we take these token names, we filter them, so each length is required to be greater than 0. Then we create a token. Token is a separate object. I will come to this in a moment. And we transform to, so that was quite useful. Once I started using ranges, I like it. I'm not saying I love them, but I like them. And they are really shortening your code. But sometimes debugging can be tricky. So finally, some other techniques which can be useful in creating such systems like this one. These are the three. First is spaceship, three-way comparison operator. It is really helping in writing clear code. Again, please take a look at some good presentations. So for source file index for debugging, there is such a structure in this Ford project. It's not that important what it does. It is just an index to the map of file names, because each token must know in the debugging from what source file it comes from. But this is interesting thing. Yeah? So if I need to put such a structure, such object into the map, I need to implement some ordering, and this is enough to do some simple ordering. This is really cool thing in modern C++. Yeah. Also this const exp, again, whatever we can make const exp is really worth considering in an embedded system. This is interesting thing. So we have two modes of operations, so no unique address. So what it does is if a member has an empty class, the compiler can eliminate it as if it were not there at all. So the thing is that the structure, even if it is empty, its size of will be 1. So why this is important? We have two versions of the software, with debug on and release, let's say. So we have such structure debug file info, but in release version debug file info is empty. Yeah, no debug information. So we have a token. So token has a name for sure, always. And sometimes it has this debug information. But sometimes it doesn't. So what is the size of this? I don't know. Okay, so if debug is on, we have 40 for the name. We have 6 for the debug file info. So we have 48 with alignment. But what happens if we have non-debug? And no unique address. So again, we have 40. Look at this. Debug is empty, but its size is 1. And again, the size of the entire data structure is 48. It plays a role because this is a stream of tokens. So it will be hundreds of thousands of such. But with this unique address, look at this, non-debugging, but compiler is able to optimize out the size of this empty. But be aware, Microsoft is always special. So why I'm writing this, because I wasn't sure why my code is not working on Microsoft, because my main development platform is Microsoft. Then I port to some embedded stuff. So it must be a special. Maybe they will change that. So that's something important. And the last thing, this is the whole realm of bit manipulations. So why this is important in embedded stuff, in software like this, look at the stack again. The stack is containing everything in the Ford. So it must be each cell must be big enough to contain a pointer to a word, but also return value of Boolean or a byte. So we need to convert values. So we put some bytes conceived as an object n, and we pop like new z. So how we do this? There is such a function, blind value array interpretation, and we have two modes of operation, because depending on the size, certainly it cannot be bigger than the cell of the stack, but it can be smaller. So in such a case, we need to cut out excessive values. So all this bit manipulation is just to put zeros. So if I'm transforming to something what is bigger from something what is smaller, this bigger part doesn't have garbage in some not filled bytes. But otherwise, we have just reinterpret cast to such a thing. And there is this useful if const exp, which can be used instead of preprocessor. But it works. But it is UB. Okay. So what we can do? We can use bitcast. I thought at the beginning, but bitcast can operate only with the same size. But we have new kid on the block. Again, start lifetime s. And this is very interesting function. And again, go into the specification from 2022. So it is to tell the compiler explicitly that an object should be created at the given memory location without running any initialization code. So look at this. If I have such a simple structure, and I wish to make such a factory function, and I am in my embedded system, I have my own memory allocators, my malloc, and I create such a structure, so I don't want any initialization code. I wish to start from this byte right away. So that's the way. And I can use the fields right here. Well, it's useful in couple of operations. But when I looked at this, you see, no compiler has this yet. But this is the way we can think of bit manipulations. Okay. So what platforms we have? So I'm just fostering using C++ in embedded system for a quarter of a century, I would say. So the big one is based on RISC-V, ESP32. Is something, it costs $5, but it is well equipped anyway. So we are using this for porting, and this is actually, this is on this computer, this board. And this is the framework. So we do external debugging, external flashing device, and so on. And this is visual code to operate with. And well, we have this compiler. But what is more interesting, total image size of the big project without any cuts is 750, let's say, kilobytes. So, but we can cut it really much more than this. And yeah, RISC-V is my favorite processor. I think it is changing the world. So, but we can, well, I mentioned this is used also to teach students. So the system made by my students was using even smaller board. So a couple of years ago, I think 2 or 3 years ago, they ported to really small 32-bit, 80 kilobit data RAM stuff. So here is the project. You have more issues I haven't touched upon, but they are very important. Custom memory management. This can be for many talks. So if you are looking for a subject to prepare, memory management is the issue, especially in embedded stuff. Modules. I ported a couple of files to modules. I like them, but still some work to do. Concepts. There are some concepts in this project. More context, const-eval, special versions, so we can make software automatically adjusted to the board. And conclusions, finally, new versions of C++ offer really cool and useful features also for embedded systems. Fourth language is a very interesting platform that allows controlling devices, but also interacting with users. And it can be really tailored to the needs. Yeah, that's the point. So it is worth ensuring tailored solutions. For example, simple smoke detector can be equipped with a simple cooperative systems. So it is more green, it is using less energy, probably less silicon. Yeah. Good projects are necessary for teaching students. So this is one of the, I am not saying this is good project, but good for teaching because it is not too big. Coroutines, yes, they can make the system cooperative, but with limitations. Ranges, if you haven't used them, just go for them. And other very useful features like concept modules, bit operations concept, at least to consider to play with them. So that's the key findings of this project. So if you are interested in teaching, there is a book available. Code is free on the GitHub. I'm working on another book. Here are the links to the projects with a couple of branches. Yeah, this is something what I was fighting for years, to use C++ in an embedded systems that really plays off. And I think that's all. Thank you very much. If you have any questions, yes, please.
Hey, thanks for the talk. I might just be too tired at this point, but the fiber example, can't that be just implemented without coroutines as well?
Sure, you can take DAF, this device, and make it like I presented. The entire Ford system worked without coroutines, but the question was if we can simplify something or have more features using coroutines. So yes, indeed we can.
And wouldn't it be more useful for the tasks to be coroutines so they can like interrupt instead of the...
Well, this way, look from the Ford point of view. This way I can have ordinary words which start and end, but if I need to do something systolically in some, okay, from period to period, I just add co-fiber and everything is starting to work periodically. That's cool. I don't need to program anything more. If you don't need such a feature, you don't need it. But sometimes you need it, just to check some signal on your board. Yeah? You can run a process without writing any loop. You just write a word to signal something, and you put this coro, and it works.
Thank you very much.
Okay. So start playing with Ford. Maybe you switch from C++ to Ford. No, this is... Okay. Thank you.